Hello viewers and welcome to a new STM32 World video. Today's video will be a little bit different than anything I've done before. It will be a KiCAD PCB video mostly. Well, it's probably going to be a fairly long one. I don't know yet, but I will, as usual, make chapters down below. So if you get bored about hearing me babble about something, you can just skip to the next channel. And hopefully, if you watch this video to the end, you might actually learn something either about KiCAD or electronics or how to do STM32 projects, because that is part of this. Now, a week ago, I posted this on the STM32 World channel on Facebook and a few other places, and it was basically, as I just described, as a 16 relay board with embedded STM32. Now, this is the board I'm going to talk about today, and the reason why I'm going to talk about this today is that I just ordered it. I don't have it yet, but I ordered it at JLCPCB. Of course, they're not sponsoring this video. I haven't asked them to sponsor this video because this is a semi-professional project that is getting paid, so that's okay. But I'm still using JLCPCB for this particular project, and I will include a link to them down in the description if you want to order something like this. So that's about it. Now, if you go back to my very first video, I stressed my philosophy for this channel, and that is to include mistakes. Because mistakes is the best learning experience there is out there. So if you don't make mistakes, you don't learn anything. So I thought it would be appropriate to post this video now about this board to give you some idea about why it was designed the way it is and my thought processes when designing it, and also going through and then I'll do a follow-up video after I receive the board, which will probably be roughly in 5-6 days. And then we'll see if it works. It might not work at all, but then I'll talk through that, and that will be an interesting discussion as well. Now, a little bit about why this board is designed and why it was made in the first place. This was not and never meant to be something selling. It is basically, the task was to do a test rig, and this is basically a one-off. There might be 2 or 3 of them, or 5 even, made, but the idea is to have a test rig which can be programmed to wire up, and the specification was that we need 64 relays that can carry 2 amps each. That was the specification. So what I thought was a board with 64 relays. Now, when you do a board like this, a lot of things can go wrong. And the idea was to, actually, I wanted to make a prototype of everything first, because then it's just duplicating that to have more. So I decided to make, I mean, you could have made a board just with the MCU and the power supply and 1 relay, and that would have been entirely possible, but that would at the same time have been completely useless. Now, I thought this board with 16 relays, I don't know if we are going to sell this, or I have no idea, but I sort of in my head designed this board as if it would be a product we could sell for home automation or whatever, anything where you need a bunch of relays doing something. So that's how it was designed, and that is the plan. And again, the purpose of this was not to make this product. The purpose was to make a test rig which would be much bigger, or 4 times exactly bigger than this board, but this is so there is some design decisions that go to having that final board and living up to those specs, which is 64 channels with 2 amps, or this, which is then 16 channels of 2 amps, but as a standalone product. So let's look at the KiCAD schematics first. And now this is pretty much the version that was ordered, and I already, and you should never, one of the mistakes I've done a number of times, you order something and then you find a mistake in the board. Like, you just have to say, okay, I have to live with that, and I have to find a way without it. And I actually already found at least one rather serious mistakes in this schematics. But anyway, let me talk you through what it is. Now, up here, we have a connector, external connector, that is actually a Phoenix connector that give the supply voltage to running all these relays. They do take quite a lot of current to run this relay, but if you look over here, we have the power bus, and we have that supply line going in through a diode, a Schottky diode, and that would be my input voltage to my voltage regulators. But you'll see I also have the V-bus going into the same one, and V-bus is coming down here from the USB connector, and that means in theory this board can be powered by USB only. It probably shouldn't for production, although to be honest, I can actually power these 16 relays from a USB current, the current about 500 milliamps. It is possible in theory, but I can definitely not drive the 64 relays in the final board. However, in my lab, my office, I have a workstation where I can develop and stuff like that, but all the electronics is on another desk where I don't actually have a PC around. So in order for development, it's convenient for me to be able to power stuff just with the USB, because then I can do the development and I can always move it over to the electronics desk for further testing. But it's convenient for me to be able to power with a USB. I can take my laptop and I can just plug it in and everything should kind of work. Now, so this voltage Vin will either come from the supply or it will come from the V-bus, and these inputs go into a switch mode power supplies, which is based on a Texas LMR33640, which is a really nice little switch mode power supply. It is nice for two reasons. Now, if we look at this, it is actually an SOIC 8 with a thermal pad, but it is actually it is quite easy to route. It is not too expensive. I believe they're about $1 a pop or something like that, and they are quite simple layout. And what is really interesting with this one is the range. It can take a V-in from essentially slightly above, like 1 volt above the output. So in this case, for the 3.3, it's like if it's above 4 volt or something like that, it'll be fine. And it can take up to 36 volts, and it will still get it down to 3.3 volt. Above 36 volt, it will go puff. And believe you me, I have seen that. It's actually quite interesting. So yeah, it's up to 36 volt. It is solid. Now, I should probably have put a Zener or something like that, or a fuse up here, or fuse and a Zener to a 34 volt Zener to make sure to protect it. But in this case, it's okay. If it blows, it blows. I can live with that. Anyway, you need the other thing is it can actually deliver 3 amps. So this one can deliver 3 amps if the input can supply that. Of course, if I power it from from USB. That will not be relevant in this case. I don't have the power delivery USB-C, power delivery electronics or anything like that, so it can go up to, well, a typical port will probably deliver up to an amp or something like that at 5 volt. But the specification is 500 milliamps. Now, I have two of these power supplies because the relays I'm using are using 5 volt. So this is the 3.3 volt, and then up here we have the 5 volt power supply, and the only difference between these two is this voltage divider. So you basically take the output voltage and you divide that so that you get exactly 1 volt at the voltage you want. You need 1 volt supplied back to the feedback, and that is it. And the switch mode will adjust itself to deliver the correct voltage to this inductor and these. So this inductor needs to be able to handle the current that you want to supply. So in this case, a couple of amps, if we're driving 64 relays, they take about 200 milliamps at 500 at 5 volts. So yeah, it'll be about 2 amps if they're all supplied, all on at the same time, which will never happen. So that was the 5 volt up here. Have one difference, and I'll get back to why that is, and that is actually the enable pin. Now, if you look at the 3.3 volt, that is pulled up to the VN, and that means this will be on the moment the VN is about 3 volt or something like that. It will start switching on and do its best. But the 5 volt one can be controlled by this EN5E signal. And here is, by the way, the first mistake I have done in this board, and that is, according to the data sheet, I'm not going to go into that right now, but believe you me, the data sheet said you cannot leave this floating. And I'll get back to where this goes, but it is actually floating. What I should have done is I should have put probably a 100K resistor from here to ground to make sure that this one was never floated. But I wanted it to be off by default until it is actually enabled and need to go on. I'll get back to why that decision is. But what I can do, I'm not too worried about it for the first prototype. What I can do is I have this unpopulated pins out here, and I can just take a through hole resistor from there to there, then I have it pulled down, and that is all hunky-dory. Now, next step in this is I put on an MCU, and the MCU is supposed to be able to control everything on this. Now, originally it was actually built around an STM32F402, which is more than enough to run this and could do everything that I wanted or needed in this case. But at the moment, as you can see from some of the earlier videos, which has been sponsored by JLCPCB, in China you have this China-only model, which is called STM32F402, which is cheaper than an STM32F103 and a lot more powerful. It's got like 4 or 5 times as much memory, 2-3 times more flash. It is just bigger and better in every conceivable way and cheaper. Now, this model does not exist in STM32 CubeIDE, but it is exactly identical, as I have shown in earlier videos, with an STM32F401. So for all intents and purposes, this is an STM32F401. Now the STM32F401 is about, I think, $3 or $2.80 or something like that. So that is more expensive than the F103, but this one is only about $1 something. So it is actually cheaper. Go figure. Now the setup here is essentially 16 megahertz crystal, and then you can see you have a LED, you have that enable pin, and here comes a problem about leaving that enable pin floating, and that is by default, until this microcontroller is initialized, that pin will most likely be a high impedance input pin, and that means that whole circuit will be floating, which Texas specifically tell you in their datasheet you should never leave this one floating. So there is a design mistake there. I should have taken one more resistor to ground here and everything would have been fine. That is about it. Now you can see in this I have two UARTs enabled. I have UART 1 and I have UART 2. I'll get back to where they go and why. I also have two I2C buses enabled. I have I2C3 and I have I2C1, and they are both enabled. I also have SPI down here, and I have SDIO enabled here. Now, hooked up to this microcontroller, let's go down here. First of all, there is these two buses which go out to a header and a UART header. And a programming header. That's all pretty much hooked up straight to the STM32. I also have down here, I have a 16 megabyte flash chip. Now, the thing about these is that you always have to keep in mind, if space is not an issue, footprints are free. I pay the same for a board whether I put this footprint on or not. And you don't have to populate them. You see that quite often in professional design. You see there's a footprint that is unpopulated. Why is it unpopulated? Well, it's like the designer was like, oh, maybe we need that one day. We might as well put the footprint in. It doesn't cost anything. So in this case, I put a flash chip so we actually have some storage which could be used for something in the microcontroller. Run a test procedure directly and store that test procedure not in the program but in an external file. I don't know. It's just a case of why not put it there. I also have, for exactly the same reason, over here I have an SD card hooked up via the SDIO. This is exactly the same circuit that I used in my SD card breakout board, so I know this working. And again, it cost, I mean, resistors cost 0.1 cent or something like that in when we put these on, and these capacitors probably cost less than a cent each. So even if I populate these, but I mean the SD card holder is about I think 80 or 90 cents or close to $1. So that one does cost a bit. This flash chip down here also costs about $1 if I populate it, but if I don't populate it, it doesn't really cost anything. And that is the beauty of this. The final element in this design are the relays. And there are 16, you can see, leaf sheet. So these are sheets, and each sheet, they are all identical. So there are 16 exactly identical relay modules. And nope, I forgot one thing I want to talk about before I did this. So each of these relays are driven by a single signal, high or low. High, the relay is energized, low, it's not. And this is all controlled by a GPIO expander. Now, I use this AW9523, which is a dirt cheap Chinese one. I think they're about 15 cents a pop. And they work really well. I use them in the LED board I made. Look for I2C LED board I made a while back, where I'm driving 5 RGB LEDs with one of these, because this one actually have a built-in LED driver. Now, let me show you one thing in the data sheet which is interesting. I have a link here to the English data sheet. So it's a 16 multifunction LED driver and GPIO controller with I2C interface. Now, it is mostly meant to drive LEDs, and that is really clever. I explained that in the earlier video. You can go back there and see it. But it can also work as a GPIO. For example, here they use it for keyboard, where they use input, but it could also be simple output. Now, one of the oddities with this, and that is what you need to learn to live with when you're using Chinese products, sometimes they have some really odd design decisions. And one of the odd design decisions on this particular board, let's see if I can find that, is down here, is that the default state of the I/O port depend on what I to C address you are using. So by default, if I look at this, you can see that I put solder jumpers and they default go to ground, both of them. But if you wanted 4, and I need 4 for the 64 relays, right? So, but for one, I just put it to ground, but I put a solder jumper on so I can experiment with putting it on the other addresses. And if you look here, if we put them to ground, everything is fine. They default to being 0. That means all the relays will be off until they are actively set to high. But it's got this oddity that if you're having one of the other addresses, for example 1, where we have a 0, 1 on the address pins, you will see that the first 4 pins are still 0, and then you will have 4 pins that are on. And that means the moment you power this on, it'll go poof, and you will have 4 relays that are on. Now, that is the reason why I, in this schematics, made the 5-volt controllable from the microcontroller. So the idea is that if we don't have 5-volt, I don't care if the relays are on or off, they won't go on until there is 5-volt to actually drive these relays. So the idea is that this will actually, the relays are off, and that gives me time to switch the mode of this one into all zeros and output, and then I can switch on the 5-volt after that has happened. So these are the 16 channels to drive the 16 relays. And now let's look at the relay circuitry, which is quite simple. Now it's using an OMRON relay, which is default off. So you have this dual pole thingy, and each of these can take 1 amp exactly. So the idea is that, remember, the specification was 2 amps for these, and that means you can just run them in parallel because you got 16 off 2, so 32 circuits in all, and you can run 1 amp on each of them, and that will be fine. This particular relay is driven by 5-volt. Let's see, do I have a link to the data sheet? I do. Is that an English data sheet? So this relay, and they are tiny, they are about 1 centimeter times 0.6, so 10 millimeters times 6 millimeter or thereabout. So let's see the data sheet. Is that English or Chinese? It is English. So essentially, well, you can go through this, but the relevant part here is that you have different models with the coils that you can find some that are rated at 3-volt, some that are rated at 5-volt, and 12-volt even. And the one I'm using is the 5-volt DC, which is rated current at 21.1 milliamps. So essentially, this circuit, which is the coil driving the relay, comes from 5-volt. By default, this one will be low, so this one will be ground. This one will be off, and that means no current is running when you switch this one high, and this one starts opening up early, but at about 2.2 volt, I think it's fully on. A very, very low resistance. We are talking a fraction of a milliohm or something like that. Or no, maybe 20 milliohms or something like that. Very low. So the moment you switch this one, you go high, and this one is then conducting. You will have 5 volt running in here and down to ground. At that point, you'll have ground down here. You will also have ground here, because this is just shorting down to ground, and that means the LED will be on. Now, once you switch this off, coils or inductors, you can't change the current through a conductor instantaneously. And that means that a current will still flow even though there's nowhere to go. So that current will find somewhere else to go. Now, first, this one will go through, become very high resistant, and that means the voltage at this point will spike up way past the 5 volt that it was originally energized with. And that means this will go poof, and there will be a nice little blue cloud coming out of it, unless you put what is known as a flyback diode. So basically, that current will then, this voltage will then be higher than the 5 volt, so this one will simply go up there and short circuit this. So that's fine. So a flyback diode to protect this or this. I don't know which one will blow first. We can try that once I get it. But my guess would be it might actually be the LED. I cannot remember the reverse voltage on these LEDs, nor do I remember the max voltage on this MOSFET. But whichever is the lowest will be the one that is blowing first. So that is about it for the relays, and all these relays are simply going out to a header where I'm using IDC headers, and they are all arranged the same. So you have relay off 0, off 1, and then the common, which is the center one, and then the on state is down here. So you either hook up on these two or you hook up on these two, depending on what state you want to use, and that is it. And each of these headers will have 4 relays with 6 signals of each. It's 24. So this will all go into these IDC connectors. Now let's look at the actual PCB, which is somewhat busy. Well, I am having ground fill on. I used a 4-layer board for this. So if we look at the arrangement of the layers, the green layer here, you can see that it wiggles around a bit. That is actually a 5 volt ground 5 volt plane. So this hook up straight to the 5 volt rail. And down here, because everything down here is 3.3 volt, we have the 3.3 volt. And the only thing on this entire board that is a little bit out of place is the GPIO expander, which is sitting over here on top of the 5 volt plane, but it is powered. Where is the power? Do I actually? Oh, it's coming in there, right? So I'm getting 3.3 volt from that and getting it in there. And that is about it. So this one is sitting out here. It controls each of the relays, which are arranged. So 1, 2, 3, 4, 5, 6, 7, 8. So they are arranged in a semicircle, kind of, around here. And over here we have all the STM32, we have all these I2C bus, UART bus, and the programming header. Down here we have the flash chip sitting there, and we have the STIO card up there. And up here we have the 2 power supplies, which are, as you can see, extremely compact. So it's a switch and the coil inductor. And a LED to show if it actually delivers power or not, and I also put in some test points, so you can actually, you have test point up here for the 5 volt, you have test points down here for the 3.3 volt. Now the layout of this one is a little bit interesting. Remember, it came out in the coil, and that is essentially the 5 volt output here. And I just, since I have that ground, the layer, internal layer, all I do is here, I just put a bunch of wires that take it down to that layer. I don't even need to put a wire on it. And I do exactly the same down at the 3.3 volt. They are just basically shorted down to an internal layer. Let's look at how this looks in the 3D viewer. Here we go. You will see it was actually a last minute decision that I ended up putting this external, so you can control this power supply externally. It was a good thing I did that, because remember I made that design mistake where the enable pin is floating. So once I get these boards, I should take a resistor, I don't know, 10 to 100k resistor, whatever I can find in a drawer, and solder that into these pins. That will make that work as intended. Up. We can see down here, if we start, we have the USB, and it goes into we have the SD card, micro SD card holder. We have the 16 megabyte flash. We have the STM32 with the relay and some decoupling capacitors and stuff like that. And up here we have the power input, which have some decoupling, some capacitors on the input. That is, they are, as you can see, bigger than most. This is a 0805 or 4, what is it called? So I got about 30 microamps sitting up there, which microfarad, which is fine. Down here we have that switch mode with a inductor, coilcraft inductor, which is quite big, and all that feedback resistor. So we have the 2 buttons, by the way, over here to control the reset. We have a reset pin, and we control the STM32 from over here. Now the relays, let's look at one that is oriented there. We can take, they're all identical, and the layout is exactly the same. So we have the 5 volt, which it just have a wire down to the 5 volt layer, and we have the MOSFET, which is basically grounding this pin. So this pins go down to ground. There's a ground wire there. So the circuit is minimal, and that will be a 20 milliamp that is running in this, controlled by the input pin, which sit over here. Or is it the other way around? I can't remember if that's the input or that. It's that one that is the input. Yeah, it's okay. And we have that diode there, which is the flyback diode, and we have a LED and a resistor, current limiting resistor for the LED over here, and they're all exactly the same. And all of these are just controlled individual by the GPIOs here. That goes to all of these relays, and that is pretty much all there is to it. So far I have discovered that one bug. There may be more. We'll see when I get it whether this is going to work as I intended. If it is going to work, I'm going to have to make the 64. I should also show that on a board like this, wait, what am I doing? I can flip board down here, F. It is important to have some proper cell screen. So I have the cell screen up here, max voltage, 125 volt AC or 60 volt DC, 1 amp per pin. Down here, we have that address selector jumper here, which I haven't really documented much, but the that's not really intended for this one. And we have all these control over here. We have an I2C1, I2C2, and UART and programming header. I should mention briefly that the I2C, the idea is that the I2C, it's easier to show here. It's easier to show here. So you basically have that I2C, which is up here. Now that one goes up, and here it will branch up, so one of them will go to the header. We have the pull-up resistors up here. One will go up to the header, so it can be controlled. That can be controlled by a Raspberry Pi or whatever you want. Externally, you can ignore this STM32 completely. You could actually make a board that wasn't populated with this STM32, or where are we here? Or this one goes down to the STM32, so you can control this from the STM32. It's optional. The other I2C port, which is it's actually I2C3, goes straight to the STM32, so you could actually make the STM32 an I2C slave, and that means this whole board, you can control it with your own protocol through this STM32. And the same idea with the UART, which is down here. So you could do a UART protocol from something externally and drive this board via the STM32. So you would need a firmware in the STM32 to control the rest of the board. The last one, which is basically my intention, would be to use a USB HIT device. So you basically make a HIT protocol, and you just plug this into USB, and you can control these relays from a web app or whatever via the HID protocol, HIT protocol. And so it's basically meant to be flexible and flexible. That is the word I'm looking for. And be able to run multiple things in multiple ways, but 16 channels driven by a USB connector or a UART or I2C, and there's two different ways of doing the I2C depending on what you need this board for. So that is revision A of this 16 channel board, and I already found a small mistake, so revision B will definitely have that. So this pin is not floating, so there will be a small resistor up here, making sure that this one is pulled low or pulled high. Pulled low. So by default, the 5-volt power supply is off, and then you have to switch that on when you have initialized the GPIO expander. So that is the thought about that. Now, I mentioned I also found another mistake, or not a mistake, but something that might not be ideal, and that is over here of the PSU. Now, again, it is important to understand that electronic design can be different, depending on what this is intended for. Now, remember, this was actually intended for an internal test rig that will be manufactured in extremely small quantities, and I'll have 64 relays that cost about 80 cents a pop. So that's already $40 or $50. Now, this coil, I am using a Coilcraft. So let's look at that one on LC. Let's see. Let's look at that one. There we have it, and you see they are almost $3 a pop. And again, so $6 for this board just in coils. I noticed it when I ordered it at JLCPCB. With the exception of the relays, it was the biggest line item on that invoice. It was bigger than the MCUs and the micro SD card holder. It was the biggest line item, and that is just silly. Now, Coilcraft is top-notch quality, and they are never cheap. So yeah, I mean, for this test rig, I'll probably will go with the Coilcraft, because it doesn't matter. It's still a fraction of the cost. However, if I were to sell these relay board, the 16 relay board that I designed here, I would definitely find a cheaper coil there. I actually found one. Did I change that? This one, let me see if I changed it already, 21. I might have done this on my laptop and not committed it yet. Let's see. 21 is the same. So this is the Coilcraft in both cases. But I found one that is actually, I think, about 20 cents Chinese coil. But for this purpose, it doesn't matter what that inductance is, as long as it's like probably above 6, and I don't care about plus minus 20% on that. So I will probably go for a cheaper. Now, the irony is that the Coilcraft is actually very small compared to the Chinese. That was about 1 millimeter more in each direction, the one I found. So yeah, no, it's still 20%. Inductors are horrible in terms of this. So yeah, it was pretty much the same specs. I think the Chinese one I found, you can see this one is 10. That was exactly the same. But here, 20 milliohm. I think the Chinese one I found was 40. So yeah, there will be a slightly bigger energy lost in that inductor with the cheap. But in this case, it really doesn't matter. So yeah, I'll go for another inductor, because I'm not going to pay $6. Okay, they'll be cheaper when we buy a bunch of them, but I am definitely going to change this inductor to a cheaper version, slightly bigger. So yeah, the mistake is this one. Another mistake is that I didn't have this one is left floating by default. That is no good. That is no good at all. Other things I would change in hindsight, or probably change in revision 2. Not really. Yeah, well, I mean, there's a couple of things that I don't know, which is why you make a prototype. Now, I have done a little bit of testing, and I think it will work. But let me explain to you. I explained earlier that I like, for convenience when developing firmware for the STM32, I like to be able to just power it with one USB cable and be done with it. I don't want to worry with the external. Now, I can live with the fact, even on the big 64 relay board, that I can't power all the relays. As long as the relays are off by default, so it will run, then I can live with, if I'm only able to drive 4 or 5 relays at the same time, I can live with that during a development phase. That is not a problem. Of course, production, you would power it with an external power supply, but I can live with that. But if you look at the schematic here, we have the VBus here, which is 5 volt as per the specification, and most USB ports are fairly precisely 5 volt. But up here, this 5 volt will go in here and go to a Schottky diode. That Schottky diode will drop that voltage with 0.4, 0.5 volt. So we only have a VIN. If I don't have a power here, I only have a VIN of 4.5 volt. And this one, in order to generate 5 volt over here, it definitely need about 5.5 volt in at a very minimum. That's why I put this one. Should be powered with at least 6 volt to be able to work. However, I tested this, and it would appear if you go below 4.5 volt, it would just lower this one, and this one will be roughly 0.2, 0.3 volt away from the input below the input, and that works all the way down. So when the input drops below 3 volt, this one will cut out and stop switching. So it will drop to 0, boom, straight away. However, in this case, I'll get about 4.5 volt, let's say 4.5 volt on VN, and that means I can expect to get about 4.2, 4.3 volt out on this side. And incidentally, do I still have that? I have it here. Let me see where I can find it. That is a little complicated to find. I can't find it right now, but I can tell you that this one, according to the specs, the 5 volt version, it should be stable on about 3.5 volt. It should be rock solid on. So I think this will work, even if this voltage is slightly below what it is supposed to be. So I think that is all I'll say. As I said, I am recording this on Wednesday, and they are about halfway through production. If I'm lucky, I'll have it Friday or Saturday more likely, or Monday next week it will be on my, and then I'll test it and I'll make another video. And if I screwed up something, I might even have a video camera first time I power it on to see if there's blue smoke coming out. That'll be fun. So yeah, I might do that, but I'll definitely make a video sometimes next week that will show this one in action, whether it works or it doesn't work. So that is about it. As usual, if you felt you learned anything from this video, please do like and subscribe below. It helps the channel a lot. I know that this is not I call the channel STM32 World, and this was more over in electronics, and but I mean, those are the kind of projects that you end up doing with an STM32, so I still think it's relevant. I think it's very relevant, actually. I think there's a lot of people who like to do embedded, but they know nothing about electronics. I think that's a mistake. You need a basic knowledge of current, voltage, resistance. You need to understand the basics to be able to have any meaningful use of embedded programming. Otherwise, it's pretty pointless. You can be as good a programmer as you like. If you can't hook it up to anything, it's pretty pointless. So yeah, if you like this video, even though it might be a little off what you normally would expect from this channel, please do like and subscribe. It helps the channel. And comments below, I will, if you, I can give a blanket challenge here. If you can find a mistake that means this won't work, please do. It would be fun if somebody pointed that out before I have the final product on the desk. But I think I found all the problems that will be there, which are not many. What am I insecure about? Well, I mean, the relay, and that I haven't actually tested that before. This power supply, I actually haven't tried this particular switch mode power supply, the LMR 33640. I have not tried that before, so hopefully they work. Texas Instruments, however, are making brilliant data sheets. They are, in my opinion, the only company on this entire planet that make better data sheet than ST Microelectronics. They make excellent data sheet. A little bit too chatty on occasion, but it is there. It is, you should read them. So I'm like, my confidence level on this PSU is better than 99%. I'm quite sure it will work. I am quite sure. I would have been worried about this one if I had tried it before, but I'm also quite sure that this will work. I'm quite sure that my STM32 stuff will work. The SD card, I've done that before. I have used this one before, so I'm quite confident that that will work. USB part, I'm quite confident that will work. So yeah, my confidence level is pretty high. I have not tried this relay before, but relays are relatively simple devices. As long as you sort of the MOSFET, I've used that before. I know how that works. And so this is a relatively simple circuit, and I'm like 99 point something percent convinced that will work as well. Now the flyback is so if you forget the flyback, you are going to run into problems eventually. So having the flyback is absolutely essential to make this work reliable over time. The problem is you forget the flyback, it will kind of probably work. Initially, it might not blow. I mean, diode up here, the LED, or even this down here, there will be a leakage current. So this current comes here, it doesn't have much energy. So it can probably go through this one. It doesn't have to generate a spark anywhere to get rid of that energy. But yeah, well, you should always put that flyback on. It's not open for discussion. So that's about it. Third time I tried to stop this video. I know I talk too much. Sorry about that, guys. So yeah, like and subscribe, and as usual, have a wonderful rest of the day.